Okay, let's start today's lecture. Now, we'll start our study of chapter 4. And the first several section of chapter 4 actually has been contained in our previous lectures, which are concerning solving homogeneous Felipic PDEs. Which is homogeneous boundary conditions. A typical problem is this heat equation. So the right hand side is a square uxx. This is homogeneous heat equation, and also the boundary condition. The boundary condition is 0 here at both endpoint of the load 0 and pi. Okay, the temperature at the endpoint are all 0. Of course, here we have the Differential boundary condition. You can also impose a Newman or Rubin boundary condition at the endpoint of the load. And the more important thing is that this is 0. Okay. To solve this problem, we first try to find separated solution or product solution. Okay. To find a product solution, we need to solve an eigenvalue problem. Maybe you have noticed that all our eigenvalue problem, the boundary condition is 0. X0 is 0, x pi is 0, or xl is 0, or x prime 0 is 0, something like this. We never solved a boundary condition. Eigenvalue problem. X0 equal to 3 and x pi equal to something. We will never encounter this. This is not an eigenvalue problem. For eigenvalue problem, the boundary condition for the x always 0. If it is not 0, then this is no homogeneous boundary condition. We have never studied this kind of problem. Also, for the equation, we always have a homogeneous equation. If you have an f here, ftx, then we cannot solve it, as we will see. Okay, but now we will start this kind of problem, how to solve no homogeneous problem. That is the topic of our lecture today. So we start with this very powerful, very important, very fundamental theorem. So it says that any good function defined on GL can be expanded as a series f and xn. Xn is what? Xn is the nth eigenfunction of the ODE. You know, to talk about eigenvalue problem of an ODE, you not only need the ODE, you also need boundary condition, such as x0 equal to 0, x pi equal to 0. Okay? But no, this is any boundary condition, but as long as it is homogeneous. Okay? So the xn is the nth eigenfunction of this ODE coupled with any kind of homogeneous boundary condition. Your boundary condition can be Differential boundary condition, can be Newman, can be Rubin, or even mixed. Okay? For example, x double prime plus lambda x equal to 0. X0 is 0, x prime pi is 0. Okay, this is mixed. At one point you are imposing Differential boundary condition. On the other point, you impose a Newman, mixed, two kind of. Okay. Anyway, any homogeneous boundary condition coupled with this ODE, you have an eigenvalue problem. Then xn is the eigenfunction. So any good function can be expanded by this series. Okay. This means what? This is sorry. Oh no. Yes. This means the boundary of the interval. The symbol means taking boundary. Therefore, that is 0 and arrow. This is not important. Just the notation. Okay. Moreover, the eigenfunctions are orthogonal. Different n if not equal to m means that x and xm corresponding to different eigenvalue. X and Xm are eigenfunctions corresponding to different eigenvalue. Then they are orthogonal. We know that this can be considered as an inner product, similar to dot product in calculus 3 we learned. Okay. When n not equal to m, this integral is necessarily zero. Without computation, you know that it is zero. This is guaranteed by this theorem. You don't need to compute this. Of course, when n equal to m, this might not be zero. This can be some quantity, maybe depend on n. Okay. Anyway, the important thing is it is orthogonal. Then with this orthogonality, we can determine the Fn. You see, in our expansion, we have a coefficient. Since this is the expansion of F, of course, we denote the coefficient by Fn. This is reasonable. So the Fn here is numbers, a scalar, not a function. Okay, Fx is a function, but Fn is a scalar. That is the coefficient of this expansion. For example, Fourier's coefficient. Okay, so how to determine this Fn? To determine this Fn, we simply multiply both sides of the expansion by xm. So Fxm equals sum Fn xn xm. Then you take the integral. Then your integral can be switched with the summation. You get xn xm and Fn. Fn can be read out of the integral because it is a constant, right? Then you get what? Yeah, my writing is awful. Maybe I will write more. So we have F equals sum of Fn xn. Then I multiply xn. Then I take integral. Okay, taking integral, the right hand side equals the Fn can be right outside, right? Because Fn is a constant, it can move out of the integration. In this step, we switch the order of summation and the integration. Then for this we apply the orthogonality. We see that this equals Fn delta. Maybe not. Equal. This is zero unless n equal to n. N is fixed. So the right hand side becomes what? The right hand side becomes Fm xm squared, right? The sum is over n. So if n not equal to m, this integral is zero. Therefore, the term disappears. Only when n equal to n, we have this might not be zero. Therefore, the result is Fm and then xm squared integral. From this, we can solve Fm. Fm is given by divided this xm squared to the left hand side. You attend Fm. Okay, so this is the theorem we will use numerous of time today. Okay, remember the conclusion. We don't prove it here, and we could not prove it here. Now, let's consider this example. Let's see how to apply this expansion theorem to solve some non-homogeneous PDE. So this is the example. F is a function xt. Phi is sine 3x. Okay. Then this is a non-homogeneous heat equation. Non-homogeneous because on the right hand side we have a F there. Okay. Then this is initial condition t equal to 0. Okay, and this is the boundary condition when x equal to 0 and x equal to pi. So this equation describes the heat phenomena on a rod of length pi. The left hand side is 0, the right hand side is pi. Okay, and there is some source of heat inside the rod described by F by the non-homogeneous term in the equation. So for this equation, how to solve it? Okay, I just reminded you, because of the presence of f, the separation of variables will not work. Okay, you can try. So if you want to try find solution u equal to xt, then substituting into the equation you have what? X. Substituting into the equation you have xt prime, that is ut, equals x double prime t, right? If homogeneous, you're done. Then you can divide both sides by xt, and then you can separate. But now we have an f, therefore you still have to write f. Maybe I don't write ftx, just f. So you cannot separate. For example, you divide both sides by xt. Yes, on the left hand side you do have t prime over t. On the right hand side you have x double prime over x. But you still have an additional extra term. You still have this term, right? This term depends on t, this term depends on x, but this term depends on both x and t. You could not say, oh, it has to equal to some constant lambda. Okay, this is why the separation fails for no homogeneous problem. So we cannot solve this problem as before. But how can we do this? How can we solve this problem? Now, we don't care. We just consider the corresponding eigenvalue problem, x. We don't separate, but we still write this eigenvalue problem and solve it. So this eigenvalue problem is precisely the one for the corresponding homogeneous problem. Now we are solving a no homogeneous equation. Pretend we are solving the homogeneous one. Then we have this eigenvalue problem. Solve it. Okay? Solve this eigenvalue problem. And we know that the eigenvalues are n squared. And the corresponding eigenfunction are sine nx. Okay? Now, using our expansion theorem I just mentioned, every function can be expanded in terms of these eigenfunctions. Right? Using this expansion, every function. But this f is a function of x. But we have a function of t and x. But for every t, maybe for every t, the x values, but t fixed for every given t. This is the function of x. It can be expanded in terms of the eigenfunctions. Right? This should be equal to the corresponding Fn. You consider this, the key point is that you consider this fixing t, you consider this as a function of x. Then you apply our expansion theorem. It can be expanded by a series of the eigenfunctions of this eigenvalue problem. This is guaranteed by our theorem. Okay, but now you should be careful, because for different t, this is different function, right? If you consider the ftx as a function of x, then for different t, there are different functions of x. So correspondingly, the coefficient here also different. So the coefficient depend on t, right? So you should write this also depend on t. So ftx equal the sum of f and t, x and x. Okay. So this is the key point. So of course our solution, the solution of our problem utx, if you fix every t, consider it as a function of x. It can also be expanded by our eigenfunctions of the eigenvalue problem. As for f, the coefficients also depend on t. Now the coefficient of this we denote by t and t. Maybe if you want, you can also denote it by u and t. Maybe it is also reasonable. Maybe it is also maybe it is also not reasonable to write u tx equals sum of u and t x and x. Maybe this is also reasonable, but just a notation. This is not essential, right? Anyway, I already write t, the coefficient of this expansion, I already write t and t. Any question about this? So our f(x) can be expanded as a series of xn. The coefficient of xn is constant. This is for a single function. But if you expand, if you consider a two variables function as a function of the second variable x, then you have to consider this as a family of functions. For different t, you have different functions of x. So your expansion, the coefficient might be different. Then the coefficient depends on t. Okay, so the coefficient should be a function of t. Okay, this is you should understand this. As before, this is the expansion of f. Okay, this is the key step to solve this non-homogeneous problem. Now our task is to find t and t. If you can find t and t, so that this u satisfies our problem, then this problem is solved. Okay, we need to find t and t. How to do this? The fn here. So since f is known, we can compute the coefficient of fn. Our formula for computing the coefficient for the expansion, we know our f is fn xn, right? We have a formula for fn, right? Then this is the formula. Apply the formula. We know that the coefficient in the expansion of f tx, that is f and t, is determined by this integral. Okay, so and this can be computed because our f tx is xt is the multiple of xt. Therefore, this integral can be computed. Of course, the value of this integral depends on t. By computing this, you consider the t as a constant because you are integral with respect to x, so it depends on t. That is f and t. So what we get? The initial condition can also be expanded. Px on one hand, it is sine 3x. This is given by our problem. Let's go back to our problem. Our problem is here. Fxt is xt, and the Px is sine 3x. Okay, this is explicit function. So Px is sine 3x, and then this can be expanded. And but the Px is sine 3x is the initial condition. Therefore, this is u0x. But u0x is what? Our utx is t and t sine and x. Now u0x is t and 0, right? T and 0 sine and x. Okay, that is our u0x here. Now it is t and 0. So then from this, what can we say? We see that t30 is 1. Comparing the coefficient, in general, the t and 0 you should using similar integral to determine the coefficient of the expansion. But in our special case, because this is sine and x and from 1 to infinity, when n equal to 3, sine 3x. So you see that t30 is 1, the other tn are 0. Without computing the integral, you can have this conclusion. Okay, this is why I choose this initial condition. Then we apply the PDE. PDE. U is what? U is t and t, x and sine and x. U is the sum of t and t, sine and x. So the partial derivative of this u with respect to t, suppose you can switch the order of summation and the differentiation, then the derivative be kind of applying to t and t. So you have t n prime. Okay? So ut is t n prime xn. Right? By our expansion of u, and then switch the order of summation and the differentiation. So you have Tn prime here. But ut is uxx plus f. And what is uxx? If your utx equals tnt xnx. In this case, your uxx is what? Your uxx is similar to tnt. Uxx is taking derivative, which is respect to x twice here. Then switch the order of summation and the differentiation. You have tnt xn double prime x. Okay, so yes, this is uxx. You switch the order of summation and the differentiation, but the second order partial derivative, which is respect to x of this, is just a tn x double prime, xn double prime. So you get this, okay? Then copy our expansion for f. Copy our expansion for f. F is sum of f and t sin and x. Copy this to our computation. Here, look at this. Then combine this. Before combine, we remember that xn double prime plus lambda and xn is 0. Because xn is eigenfunction corresponding to lambda n. So the xn double prime replaced by minus lambda n xn. Okay, then copy the term of the second series here. So what can we see? Comparing both sides, what we have? We have the right-hand side. Let's continue our computation on the right-hand side. The right-hand side become sum of minus lambda and t and t plus f and t, then x and x, right? You combine these two and which draw the common term x and x outside. So you have the right-hand side is here. So comparing the both sides of this equality, sigma tn prime t x and x equals this times x and x. Therefore, this has to be tn prime. Agree? This has to be tn prime. So we obtained an ODE for tn prime. For tn. No homogeneous linear ODE. The non-homogeneous term f and t is the coefficient of the expansion of ftx as a function of x. Our ftx equal sigma f and t x and x. That is the f and t. Okay. So if your u satisfies, if your u can be expanded in this way, then this TNT has to satisfy this ODE. So the TNT can be obtained by solving this ODE. But to solve this ODE, you still need initial condition for this TN. But we already know that okay. We already know that Tn0 is 3 when n is 3, and when n is not 3, Tn0 is 0. By the expansion of the initial condition, we have this initial condition for every TNT, right? And the lambda n is n square. F and t will have computed f and t, which is given here. So this is a initial problem for first order linear ODE, non-homogeneous. But we can solve this. The solution is given by this. Okay, this is what we learned in ODE. You should have you know how to solve y prime plus pxy equal qx. And y0 equal to some function. Y0 equal to some y0. There is a formula to solve this initial problem for the ODE. Right? Applying this formula to our case, you see that the solution is given here. Therefore, our solution, and this is simply a computation because I can compute it with this integral, which given here. The detail is not. We will have no time to do this calculus 1 computation here, okay? And eventually, this is the precise expression for TNT. So our solution is what? Our solution, I copy our TNT here. Our solution is given here. Our solution UTX is the TNT here times the eigenvalues, eigenfunction sin nx. Okay, so this is solved. And this anyway, this is just some transformation, not important. So this is solved the non-homogeneous problem. Okay, the idea is that I don't care what kind of a problem you are. I imagine I am solving a homogeneous problem. Then I have a corresponding eigenvalue problem. Then I expand the non-homogeneous term, the unknown function u, and also the initial condition in terms of the eigenfunctions. Okay, then I just need to determine the TNT. That is the coefficient of the expansion of our solution. But the TNT satisfies a corresponding ODE, initial value problem for the ODE. So the TNT is solvable, we can solve it. Okay, that is how we solve non-homogeneous PDE. Okay. Now, let's have a look on another example. In the previous example, to make explicit, I have assumed that f is given by an explicit function xt, and the initial condition is a given function. But for our general discussion, we don't need to given you the f and the phi. Once this data is given, you need to compute the integral. That is not the main task of our course. So for our next example, I don't care what f and the initial condition is. I simply say that I have no homogeneous term ftx. This is my wave equation. Okay, and this is what? This is the initial displacement when t equal to 0. So the wave equation describes the stream. Okay. So the initial condition, initial displacement is gx, given by a function. Now, this red curve is the graph of gx. That is what the stream located at the initial moment. But for the wave equation, you not only need the initial displacement, you also need the initial velocity. Well, the initial velocity is hx. Okay, so these two equality are the consist of the initial condition, then boundary condition. So the boundary condition on the left hand side, u is 0. On the right hand side, the derivative is 0. So the left hand side is the initial boundary condition. The right hand side is Newman. Okay, so this is a initial boundary value problem for non-homogeneous wave equation. Okay, how to solve it? As before, we directly write down the corresponding eigenvalue problem. Because our boundary condition for u is Dirichlet at the left endpoint, Newman at the right endpoint. So the eigenvalue corresponding eigenvalue problem for the capital X is given here. The left hand side is x0 equal to 0. The right hand side, because you have a derivative which is respect to x for you, correspondingly you have x prime pi is 0. Okay. So you should know what kind of boundary condition corresponding to your eigenvalue problem. Okay, depends on how to impose the boundary condition for the eigenvalue problem. Depends on the corresponding boundary value condition in your PDE problem. Now, this eigenvalue problem, we know that we can solve the eigenvalue and the eigenfunction. And although I have typed the computation here, but I should omit it. It is time consuming. Anyway, so eigenvalue is what? Eigenvalue is lambda n here, n from 1 to and so on. And then the corresponding eigenfunction is sine. Okay, you can do this. You know how to do this. We have encountered many this kind of problem. So anyway, you know how to solve the eigenvalue problem. Okay, so this eigenvalue problem. You know how to solve it. It turns out that the eigenvalue is here. Eigenfunction is sign. Okay. Now, this is the first step for solving the non-homogeneous wave equation. Now, we expand our solution. We consider our solution U under the non-homogeneous term ftx as function of x. You can consider them as a function of x, which is a parameter t, right? So since they are function of x, they can expand in terms of these eigenfunctions. Expand as a series out of these eigenfunctions. Of course, the coefficient depend on t. Different t, your u is different function of x. So the expansion of the coefficients will be different. Of course, depend on t. Therefore, function of t. Okay, this is the expansion for u. And also you have the expansion for f as well. The fn can also be determined because you know f. In your problem, f is given. So principally, you can compute this integral to obtain the expression for your f and t. Okay? So now our PDE becomes what? Our PDE, as I said before, since UTX is sum of, I'm writing too large. UTX is the sum of Tn T, x and x, right? Therefore, UTT is taking derivative which is with respect to t twice. Okay, if you want to compute the UTT, you take TT twice. Then you switch the order of summation and the differentiation. Eventually, you can obtain a Tn double prime. Okay, so UTT is Tn double prime xn. But according to the equation, UTT is uxx plus ftx. So, but uxx is what? Uxx is Tn xn double prime. Okay, and copy the expansion for f. Where the coefficient fn, we already know. We have a formula to compute f and t. We know that. Okay. Now applying the result that xn is eigenfunction corresponding to lambda n. So xn double prime plus lambda n xn is 0. Okay. So the xn double prime here can be replaced by lambda n. So minus lambda n. Sorry, there's no prime here. We don't need double prime here. I just copied the code and modified it, but I forgot to remove the double prime. Okay, and then copy the expansion for f. So, so what we get from this what we get, we can see that sigma Tn double prime xn equals sigma Fn minus lambda n Tn xn, right? From this equality, the left hand side is Tn double prime xn. The right hand side is Fn minus lambda xn, lambda n xn, Fn minus lambda n xn times xn. Okay, so from this we see that Tn double prime plus lambda n Tn equals Fn. Compare their coefficient. So this should equal this. That is this ODE, second order ODE for our coefficient Tn, right? So this is the consequence of the PDE because here we applied the PDE. Okay. Now we deal with the initial condition. Initial condition, the initial displacement t equal to 0, u0x. This is our initial function, gx. But on one hand, this is gx. On the other hand, u0x equals the sum of Tn0, x and x. In the expression of Tnt, let t be 0. You obtain the u0x equals this series. So you can expand your Gn. Maybe not. we consider another initial condition, the initial velocity. Similarly, ut 0x equals t implied 0, right? So, but we know that g equals gn xn x, and the hx equal hn xn x, and the coefficients of gn and hn can be computed by integrating some quantity, some function related to g and h. G and h are given, therefore the coefficient of g and hn are also available. Okay, for example, your gn is what? Gn is maybe xn squared gxn. We have an integral expression for the coefficient, right? So the gn and hn are available. So combine everything together, we have what? We have this ODE for Tn. This is second order ODE. And this Tn satisfies what? Gn is the sum of Gn xn. Therefore, Gx is the sum of Gn xn x. This is the expansion for the initial function, the initial displacement. But on the other hand, Gx equals Tn0 xn x. Comparing these two, you find that Tn0 is Gn, right? Similarly, compare the expansion of h here and here. You know that Tn prime 0 is Hn. So we obtained a conclusion that if you can be expanded as, yes, if your u is expanded this way, then the Tnx is what? Tnt is what? Tnt satisfies this initial problem for second order linear constant coefficient non-homogeneous ODE. We can solve this problem. Principally, we know how to solve this ODE and find the Tn. Once you find the Tn, then the resulting u here, is the solution of our non-homogeneous wave equation. Okay. So this is the method of solving non-homogeneous equation. But the boundary condition. Oh, yes. I already talked about this. This is the expression for Gn and Hn. Anyway, we have solved the non-homogeneous wave equation. Okay, but now we have solved two non-homogeneous PDE. One is the heat equation, the other is the wave equation. The PDE is non-homogeneous, but the boundary condition still homogeneous. Okay, if the boundary condition is not homogeneous, we could not construct the eigenvalue problem. Without the eigenvalue problem, you could not expand your U, your F, and everything in terms of the eigenfunction. So the boundary condition is homogeneous, is crucial for doing this. But you could not expect all the problem you encountered has homogeneous boundary condition. If the boundary condition is not homogeneous, what should we do? Okay, that is a new problem. Now we'll talk about this new problem. Oh, no. Before that, we solve another non-homogeneous PDE. This is the Poisson equation. Okay. Poisson equation. So uxx plus uyy equal f, non-homogeneous term. And the boundary condition is what? So this problem, x is from 0 to pi. Y is from 0 to 1. So the second line is the boundary condition for x equal to 0 and x equal to pi. X equal to 0 means what? So our domain is this rectangle. Okay? This rectangle is the domain where the problem is seeking Now when x equal to 0, when x equal to 0, u is 0. On the left boundary, u is 0. On the left boundary, u is 0. On the right boundary, is Newman. The partial derivative of u, which respect to x, is 0. On these two parts, x equal to 0 and x equal to pi, we have a homogeneous boundary condition. On the upper and the bottom and top boundary, they are given by g and h. Maybe here u is g and the uy is h. Okay, that is the problem. How to solve it? Now this is no homogeneous PDE. Okay, no homogeneous. How to solve this no homogeneous problem? So firstly, you need to find an eigenvalue problem. Eigenvalue problem. So the eigenvalue problem, you can, as I said in the videos about our test last week. Okay, you need to determine you should consider this eigenvalue problem or y double prime plus lambda y equal to 0 and y something. You should determine your eigenvalue problem is about x or about y. But for our problem, we need to consider the eigenvalue problem for x because with respect to x, you have homogeneous boundary condition. X equal to 0, u is 0. Correspondingly, x0 is 0. X equal to pi, ux is 0. Therefore, correspondingly, x prime pi is 0. So this means that we need to consider the eigenvalue problem for x, not for y. For y is 0. You do not have a 0 condition. Y is 1. You also do not have a 0 condition. So you could not make an eigenvalue problem for y. So you have to work with this eigenvalue problem for x. Okay, and this we can solve. The eigenvalue is given here. Actually, this is the same as the previous problem, the wave equation. That is the wave eigenvalue and eigenfunction. Now we expand everything in terms of the eigenfunction. So uxy, consider uxy as a function of x. For every given y, uxy is a function of x. Therefore, it can be expanded as a series constructed from the eigenfunction x and x. The coefficients depend on y. Okay? And your f, the same is true for f. F is also a series of, fxy is also a series of x and x. The coefficient depend on y. Okay? And also, your g, your boundary condition on the bottom and on the top are also expanded in terms of a series of xn. Okay? You can expand this. Here, fn, y, and the gn and the hn can be computed by integration. We have formula to compute this. Okay? Okay? Then we consider our PDE. Our PDE is fxy equal uxx plus uyy. Now, fxy is this series. This equals uxx plus uyy. But u is what? Uxy is the sum of what? Your uxy is the sum of y and y, x and x. Okay, so uxx is what? What's uxx? Uxx should be sum of y and x and double prime. Okay, so this is uxx. You can take in derivative here twice with respect to x, but switch order of summation and differentiation. Eventually, you take in derivative inside. but inside leads to xn double prime. Okay, we have to do this numerous of time. And for uyy is yn double prime. Okay, U is a sum of yn xn. Therefore, taking derivative which is with respect to y, then taking derivative inside which is with respect to y, leads to yn double prime. Okay. Then you apply the result that xn is eigenfunction. Xn double prime plus lambda n xn is 0. So the xn double prime here can be replaced by minus lambda n xn. So you get yes, you get here. You get minus lambda n xn. I switch the two terms. I copy this term here. Then this term I use this fact. Xn double prime equals minus lambda n xn. Copy it here. Okay. So from this we can see what can we say? We can see that from this we see that compare the let me see. Yes, the right hand side we can combine and then withdraw the common term xn here. Then we compare the coefficient. We see that compare the coefficient. We see that yn double prime minus lambda n yn equal f. Okay. Then we consider the expansion for G. G expanded as a series of xn. The coefficient is gn. But the G is ux0. And the ux0 is what? That is y equal to 0. That is sum of yn0 xn x. Okay? So this is the expansion of G, where gn is computable. We know what gn is. But the G is ux0. But the u is the sum of yn y xn x. So ux0 is yn0 xn x. So this means that yn0 equals to 0. yn0 equals to 0. Okay? Similarly, we consider the expansion of H. The coefficient is Hm, which can be computed. But Hx is what? Hx is the partial derivative of y at y equal to 1. But uy equal to what? Uy equal to yn prime xn. So this equals yn prime evaluated at 1 times x and y x. Okay. So this means that yn prime at 0 equal Hn. So all this consists of initial value problem for a second order linear non-homogeneous ODE, which unknown function yn. Okay. So we obtain this problem. This is the ODE that is here. Okay. Then the initial condition yn0 equal to gn, yn prime 1, yeah, equal to Hn. Sorry, this is not an initial value problem. It's a boundary value problem. Because 0 and 1. If you are yn0 equal to gn, yn prime 0 equal to Hn, that is initial value problem. But now yn not yn0, instead it is yn prime 1. So I make a mistake. This is 1, not 0. Okay? So this is not an initial value problem, but it is a boundary value problem. But it is also solvable. Okay? Although it is not our familiar initial value problem, it is still solvable. Why? Because you can find the general solution of the ODE. This is a second order the linear constant coefficient ODE. Definitely can be solved. The general solution of the ODE, yn equal to something. Yn equal to an yn1 plus bn yn2. yn1 and yn2 are the linearly independent solution for the corresponding homogeneous ODE. So the general solution for this non-homogeneous ODE is the general solution of the homogeneous ODE plus a special solution of the non-homogeneous ODE. Then you have a yn star. So this is the general solution. Okay? yn1 and yn2 are two solutions linearly independent for the corresponding homogeneous ODE. Yn star is a special solution of the non-homogeneous ODE. Then this gives us the general solution for the non-homogeneous ODE. Then using the two conditions, yn0 and yn'1, you can determine the coefficient of an and bn. Then you obtain the yn you want. Anyway, principally you can solve this problem and obtain the yn. So which the yn obtained here, you are need to the we obtain the solution for the PDE problem. Okay. So this is our Poisson equation. Okay, non-homogeneous. Then which the yn. This is the solution. Which the yn I just talked about. This is the solution of our non-homogeneous problem. Okay. Well, this is time. So this is what? This is a problem. The equation is non-homogeneous. The boundary conditions are also not homogeneous. In our previous problem, okay, in this problem, the initial condition at x equal to 0 and x equal to pi are homogeneous. So we can have this eigenvalue problem and solve it. Okay, but for our next problem, this problem, the equation is not homogeneous. And the x equal to 0, x equal to pi, not homogeneous, phi, cy. And the y equal to 0, y equal to 1, also not homogeneous. So we could not have the eigenvalue problem to work with and solve the problem. Okay, what should we do? Well, this is also solvable. We applied the principle of superposition. This problem can be decomposed into two solvable problems. One is homogeneous boundary condition, which no homogeneous PDE. The other is also homogeneous PDE and a homogeneous boundary condition. So the solution of this completely non-homogeneous problem can be written as U1 plus U2, where U1 is the problem of our previous equation. Our previous problem is here. Uxx plus uyy equal f, u0 y equal ux pi y equal 0, ux0 equal gx, uyx1 equal hx. Okay, this is the problem we solved already. Now, U1 is the problem of this. Is the solution of this problem we already solved. U2 is what? U2 is this solution of this problem. The equation is homogeneous, and the boundary value condition for x equal to 0 and x equal to pi are not homogeneous. Are the corresponding condition given here. But the condition for y equal to 0 and y equal to 1 is homogeneous. Okay? It is easy to see that if U1 is the solution of this, and U2 is the solution of this, then U1 plus U2 is solution of our completely non-homogeneous problem. You see obvious? Know that this is also solvable. But for this problem, the corresponding eigenvalue problem is a problem about y, not for x. Because y is 0 and y is 1, we have homogeneous boundary condition. So the corresponding eigenvalue problem for U2 should be y double prime plus lambda y equal to 0. Y0 is 0. Y prime 1 is 0. Okay? To solve this problem, to get U2, you need to work with eigenvalue problem for y. Okay? The reason is that y equal to 0 and y equal to 1, we have a homogeneous boundary condition. But for this problem, that is the problem we just solved, we need to work with eigenvalue problem for x. Because for x, only for x equal to 0 and x equal to pi, we have a homogeneous boundary condition. To make the eigenvalue problem, we always need homogeneous boundary condition. Okay? And then it is easy to check that this U1 plus U2 is the solution of our problem. Maybe we can make some small computation to check this. So, you see, Uxx plus Uyy equal to what? Equals to U1 xx plus U1 yy plus U2 xx plus U2 yy, right? Agree? U is U1 plus U2. So Uxx is U1 xx plus U2 xx. Uyy is U1 yy plus U2 yy. But U1 xx plus U1 yy is f. Because U1 is solution of this. So this is f. And this is 0. Because U2 is solution of this homogeneous PDE problem. So Uxx plus Uy is f. So their sum U1 plus U2 satisfies the PDE. Okay? For the boundary value problem condition, for example, let's check U0y. U0y is what? It's U1 0y plus U2 0y. But U1 0y is what? U1 0y is 0. U2 0y is py. Okay? U1 is solution of this. U1 0y is 0. U2 0y is phy. Therefore, their sum is phy. So their sum satisfies the boundary condition at x equal to 0. Okay? And similarly, you can check the other three. You know, the boundary consists of 4 segments. We already checked one of the segments. You can similarly check the other 3 segments. So our claim, their sum is the solution of our completely non-homogeneous problem. It's verified. Okay? So this problem. Now, next we talk about non-homogeneous boundary condition. Non-homogeneous boundary condition. Okay. Of course, for non-homogeneous boundary condition, or for the Poisson equation or Laplace equation, we don't need to consider non-homogeneous boundary condition. At least we can using this trick to solve it, because this is completely non-homogeneous. Okay. But of course, the method we will talk about also applied to this problem. Okay. And it should be simpler than what we did here. Okay. Let's see how to delve into the non-homogeneous boundary condition. We demonstrate the idea by some example. Now this is a non-homogeneous PDE wave equation. Initial displacement is given by gx. Initial velocity is hx. This consists of the initial condition. Then boundary condition. Previously we solved homogeneous boundary condition, but now the boundary condition is not homogeneous. So suppose it is ut0 is phi t and ux t pi is ct. So we are considering a string of length pi. Okay, so at both endpoints, x fit t values, then the displacement also values depending on t. And okay, so this is no homogeneous boundary condition. How to do this? The idea is that we try to find an auxiliary function satisfying the same boundary condition. You know, we have a no homogeneous boundary condition here. We construct a function satisfying the same boundary condition. Then we consider our solution subtract to the auxiliary function. Then the resulting function will satisfy homogeneous boundary condition. Then we can solve it. That is the idea. So that is what I said. We find the function eta. What eta should satisfy? Eta satisfies the same boundary condition as u. That is, eta t0 is phi t. Eta, the partial derivative of eta, which means vector x, where x equal to pi, is given by psi t. This is what we mean by eta satisfying the same boundary condition. Okay? Which this eta, we consider, but is there such a function eta? We want to find a eta satisfying this condition, but is there such a function? Does such an eta exist? Okay, this is the problem, but it does exist. For example, we can take eta to be phi t plus psi t x. We want to be as simple as possible. So why we construct such an eta? You see, the partial derivative. So you consider t as a fixed. You simply consider eta as a function of x. Okay, the t you consider as a constant. So the partial derivative at pi equal to psi means that eta prime pi equal to psi t. Okay, therefore, the most simple is eta tx. Eta x equal to psi tx satisfy the requirement that the derivative at pi equal to psi t. But you still need to add 0 to be phi t. Therefore, it's a line. Okay, this is not difficult to imagine the idea to construct such an eta. So having obtained such an eta, we consider its way, that is subtracting eta from our unknown function u. Eta is given. Now we obtain a function v. Once you know what v is, you know u. Okay? Let's see what v satisfies. Now, the first thing to check is the boundary condition. So when x equal to 0, vt0 is what? Vt0 is Vt0 equals ut0 subtract eta t0. But ut0 is phi t. Eta t0 is also phi t. So this is 0. Okay, this is why we need eta to satisfy the same boundary condition as u. Now, we satisfy homogeneous boundary condition. And similarly for pi, right? So the initial condition for v is what? v0 x equals u0 x subtract eta 0 x. u0 x is what? Gx. u0 x is gx. Eta 0 x is what? Eta 0 x is phi 0 plus psi 0 x. Let t be 0 here. You get eta 0 x. So this is a new function of x. This is our new initial displacement, right? Denoted by g tilde x. Similarly, we consider the initial velocity. Again, this initial velocity is a function of x. ut0x is hx, but eta t0x is what? Eta t0x. So eta is here. So eta partial derivative of eta, which is respect to t, is phi prime eta phi prime plus c prime. Evaluating at t equal to 0, therefore phi prime 0 plus c prime 0. So this is the initial velocity for our new function v. This denoted by h tilde x. Okay. And for the PDE, what happened to the PDE? For the PDE, we also now VTT subtract uxx equals UTT. This is UTT VTT. Remember, V is U subtract eta. So VTT equals UTT minus eta TT. Then UXX minus eta XX. Then you simplify. You see that the UTT and the UXX is given FTX. Then eta TT, our eta is what? Eta TX is phi T plus CTX. Okay, therefore eta TT is phi double prime T subtract phi C double prime TX. Anyway, you can compute it with this. But this is simply a new non-homogeneous term denoted by f of theta. So this V, in conclusion, this V satisfies this new wave equation, non-homogeneous wave equation. And this new boundary initial condition, this is the displacement and the initial velocity. Also, the new boundary condition. But now the new boundary condition is homogeneous. And you can solve this using the method we discussed before. You can solve this for V. Having a potential V, our solution U is simply V plus eta. Okay, so this is how we deal with non-homogeneous boundary condition. Right? Now let's consider another example. Here this is a homogeneous wave equation. So this is the initial condition, and the boundary condition is Newman. So this is a stream. This is a stream of length what? 2, right? Because from here we know that 0, and from here we know that this corresponding to x equal to 2. Therefore, the string is of length 2. The left hand side is x equal to 0. The right endpoint is x equal to 2. So this is no homogeneous boundary condition. Okay. So this is no homogeneous wave. This is a homogeneous wave equation because the equation is homogeneous, which no homogeneous boundary condition. Okay. So we can apply our previous method idea to solve this. But this problem is different from the problem we just talked about. Okay. The problem we just talked about. On the left endpoint, we have the deleted boundary condition. On the right endpoint, we have what? We have a Newman boundary condition. Both of them are no homogeneous. Okay. Now our problem. Currently, we encounter this problem. The left endpoint is Newman. The right endpoint is what? Robin. Okay. But I remember Robin, this is to be positive. Anyway, who cares? This is a kind of boundary condition. We don't care about its physical meaning. We just solve it mathematically. Okay. So how to do this? How to construct your eta? The idea, the key point is that your eta should satisfy the same boundary condition. Therefore, you should construct an eta satisfying at the where x equal to 0. How the derivative with this delta x is 10, the same. And when x equal to 2, eta x subtract eta 2 equal to 3. You should try to find such an eta. How to find such an eta? We want to find as simple as possible, but how to find it? Eta x is 10. Eta x is 10 means that if you want your eta, if you want your graph of the eta is a line, then the slope of the, the eta x is the slope of the line. of z equal eta. Right? So the slope is 10. So you can consider you can assume that your eta tx equal 10x plus some b, maybe depend on t. You can do this, right? Because the partial derivative which in respect to x is 10. So it is reasonable to assume that the graph of the eta as a function of x is a line. The slope is 10, therefore 10x. But still have a constant term. But it depends on t. We assume that it is bt. Then such an eta already satisfies this condition. So you want it to satisfy this. This is what you want. So can you choose a suitable b such that this is true? So you can try. You can try to do this. If your eta is given in this form, we compute this eta x substrate eta is what? Eta x is 10. Substrate eta is 10x plus bt. But your x is 2 because you are working with what? When x equal to 2. So the x here is actually 2. So the bt satisfies 10 minus 20. 10 times 2 is 20 plus bt. This is equal 3. Okay? This quantity is precisely eta x minus eta, evaluating at x equal to 2. But by our boundary condition required, this is 3. Therefore, 10 minus 20 plus bt equals 3. So it turns out that bt is minus 13. So this is how we construct this eta by the geometric consideration. So usually the eta we used, we want it to be as simple as possible. The most simple function is what? Constant function. But if you slightly complicated, you have a linear function, ax plus b. Okay? If you could not find ax plus, you could not find function of the form ax plus b satisfying your requirement, maybe you can consider quadratic function, ax squared plus bx plus c. Maybe. Okay. Anyway, usually these three kinds of function is sufficient to satisfy your boundary condition. Now, for this problem, having obtained this eta, our problem consider the v equal to u substrate eta. Then this new unknown function satisfies the corresponding function, which homogeneous boundary condition. But the type of the boundary condition is the same as the initial problem, except that it is not homogeneous. So this problem, the left endpoint of the string is Newman, the right endpoint is maybe Robin. But I remember for Robin, this should be positive. The coefficient for u should be positive. So because this is a negative sign, maybe it is not suitable to call it Robin boundary condition. Anyway, this is not important. Okay. So in conclusion, no matter the equation is not homogeneous or the boundary condition is not homogeneous, we can always solve the problem. So at this point, at this moment, we can say that for the three big PDE, no homogeneous equation and no homogeneous boundary condition, we can always solve it using mainly the expansion. By the way, I should remind you that previously when we solved the homogeneous problem, we use what? We use the separation of variable to find the product solution. Actually, after today, we should know that this is not necessary. Even if the equation is homogeneous, for example, your f here is 0, right? Even if the equation is homogeneous, our method still work, right? The difference is that because f is 0, now here is also 0. Therefore, every fn is 0. Okay, then the resulting ODE for the Tn are all homogeneous. Then you still get the solution. You don't need to separate the variables. That means our method for solving non-homogeneous PDE works for homogeneous one. Okay, so from now on, when we solve homogeneous problem, we can use the expansion method introduced. Okay, let's stop here.